Thank you very much for introduction. The motivation of this talk is that several years ago, one of my co-author, Dr. Takagi, mentioned that there is an internal defect in ignition capsules. And he showed me that picture, electron microscope picture, and I was so shocked that I started to analyze that internal defect. First of all, the mode analysis. I made a mode analysis of that defect. That is number 2. And we have calculated influence of this internal defect to ignition burn. And finally, I would like to propose 2 solutions. One is emulsion technique, which is free from such a internal defect. And 4-2, the second solution is more revolutionary. That is from shell implosion to a solid sphere implosion. So let's start from this person. This is a father, one father of inertial confinement fusion. As I indicated here, where is, okay. As indicated here, the DT fuel mass is proportional to rho r cube, and since we have to make rho r constant, that should be larger than alpha particle range, so that then the fuel mass is proportional to the inverse square of density. So without compression, that becomes a hydrogen bomb. But if we have 1,000 times or 10,000 times liquid density, then the fuel mass, that means a fusion output is tremendously reduced to control. So how can we do that? First of all, in top left, DT, a plastic capsule containing DT ice is irradiated either by laser or X-ray, and then surface part is ablated, and the inner part is imploded, and at the maximum compression time, the D and T fuse to produce alpha and a neutron, and that generates the ignition, and the burn wave propagates through the main fuel. As everybody knows, the largest obstacle of this scenario is quenching of hot spark by hydrodynamic instabilities. Since there is a surface imperfection, either by target roughness or imprint of laser non-uniformity, and then in the middle, during the acceleration, the light ablated material is pushing heavy fuel, and that means that is hydrodynamic unstable. So radiator instability grows very much. And at the final stage, that is deceleration phase, outer surface perturbation transferred to inner surface to be an initial seed of a deceleration phase instability. And since a hot spark, light hot spark, push the heavy main fuel, then it becomes radiator unstable again. And if the perturbation is large enough, that hot spark is completely destroyed and quenching the ignition. This is the picture Dr. Takagi showed me a couple of years ago. In bottom left, that is a surface which is produced by coating process of plastic target before polishing. Of course, by using for ignition experiment, one has to polish this surface. However, we have to know how this, I call dome, how these domes are generated. That is shown in middle. Plastic CH, 2CH, usually falling down on a substrate, but in some CH can meet before coating and then drop onto the substrate. That makes a seed of imperfection, and that grows like cone. So even if the surface is polished perfectly, there is a structure inside the plastic. And if this cone has a same density as the others, there should be no problem. However, if we look at the optical microscope in right, you can clearly see the cone-like structure plus some dome. And this means there is a refractive index difference in the cone. That means the density difference. So we are trying to analyze or to model such a defect by using a standard technique of Legendre polynomial expansion. This is the target we suppose. There are many dip. And this dip is supposed to have a shape of a cone with a angle, full angle of theta 0, which is measured from the center of the target. So suppose radius of 1,000 micron, that is NIF target, and suppose theta 0 is 1%, then the defect size diameter is only 10 micron. And that 10 micron is a problem. I don't want to go into very detail, but it's very simple mathematics. The sigma L is a mode amplitude, and that is combined to the single defect mode amplitude AL times DL. DL is a distribution function. It's, if you are familiar with laser fusion, the Rochester's Skupski made a very similar analysis on the laser beam pattern on a spherical target. I just use his theory. And the distribution parameter or distribution function DL is finally becomes a root, and n is a number of defect, n times defect volume, and single defect amplitude, that is AL, which is approximated by a Gaussian type with L node as a FWHM L mode. And then these two combine into final sigma L, that is mode amplitude for this problem. I made two formula, that is one is Gaussian and another is cone. It's almost identical. And as I mentioned, the distribution factor is nearly constant all over the L mode, and a single defect amplitude divided by some statistical number, that is 2L plus 1, that is nearly Gaussian. And if we go to high theta 0, small theta 0, I'm sorry, small theta 0 is a small defect, and that has a very broad mode component. And the final mathematics is assumption. I assumed since there is a dome, that means the volume is larger than usual. So the density should be smaller than average. So I assume this dome part density is reduced by this dome part. So it's typically 0.1% or so for NIF for a thickness of 200 micron, and what else? And theta. I'm sorry, this is not theta, but theta in actually 1%. And this is a comparison between the NIF standard spec shown in red, and this mode amplitude, which I made analysis from number of dots from 10 to 1,000. So there is some defect, which is very important L mode number. It's just above 100. And it is a most dangerous mode number in implosion. And unfortunately, since I don't have a very detailed simulation results on National Ignition campaign, so I just used our high gain target design. That is 1/3 micron laser, 5 megajoule. It's a relatively big laser. And 1D fusion yield is more than 400 megajoule. So the gain is 80. And if we put NIF target spec, and then that is reduced to a little bit below 300 megajoule. So what happened? If we increase the number of dots, look at the red line, for example. This guy has 10 micron dots. And if 100 dots is okay, neutron yield doesn't change at all. But if we increase the number from above 100 to 1,000, it's suddenly drop to 0. That is quenching of thermonuclear ignition. And same thing happened. If the size is only 7 micron, although we need a much more number of dots, but still, same thing happened, the quenching of ignition. As a supplement, I also made a field tube analysis with a few micron diameter. So the theta 0 is a 0.1%, so a couple of micron. It reduced neutron yield very much. So it's dangerous, as many people know. So question arises, why are those defects latent? Nobody from Livermore mentioned about this and didn't talk about that. I thought, phase shifting diffraction interferometer. That is typically many people use for inspecting target. PSDI is utilized to measure this internal defect. Although the lateral resolution has to be much better than the defect size, that is obvious, but it is only comparable to the defect size. For example, theta node 0.005 to 0.01, and R node 1,000 micron. And that means the defect diameter is only 5 to 10 micron. And that is comparable or even smaller than the lateral resolution of PSDI. And therefore, the defects are significantly blurred, resulting in underestimated defect depth. So, what's the solution? Solution number one. Our former target innovator, Dr. Takagi, he provided, he can provide ignition capsule made by density matched emulsion technique. That is completely free from such internal defect. His way is water globule surrounded by oil solution. In oil solution, the CH is solved. And then the another water reservoir. His point, before Takagi, this technique generates very non-uniform plastic shell because the density of oil phase and water phase is in general different. However, he found, if these two densities is completely matched, then the sphericity should be improved dramatically, and it was. And this is one of the typical plastic shell which we have used in our high-density campaign 30 years ago. And it works. And he has recently, again, innovated a technique for multi-layer capsules with silicon and germanium doping with this technique. And his target is almost ideal. I have carefully inspected the mode amplitude with from 1 to 3,000, and the total quad sum of mode amplitude is only 18 nanometer, so pretty good target. All right, so I think he is pretty happy to help the ignition, because without ignition, we can't survive. The second solution, the original ICF targets were solid sphere. When I was a student, I read the Ray Kidder's paper, very good paper. And in which the multiple shocks were designed to simultaneously collide at the center of the target. What did I write? To simultaneously create a high-density fuel and high-temperature hot spark at the center. And in mid-70s, as far as I remember, it was recognized that the central hot spark created by this way is too small. The community then shifted to use shell implosion instead of ball. However, ignition schemes, we have to recall that ignition schemes such as fast ignition or shock ignition that separate implosion and ignition do not need shell implosion. You know, since a central ignition, we need a hot spark in the center, we have to use a shell. But if one can make a hot spark externally, we don't have to use a shell at all. So my punchline is backing to solid sphere that tremendously relax hydrodynamic constraints because there is substantially no target acceleration, therefore no Rayleigh-Taylor instability. And this is our 2D simulation with the same mass. The top is just a ball, solid sphere, and the bottom is a standard shell with a 10% laser non-uniformity. With 10% laser non-uniformity, shell is almost broken, but you know, ball is very stable. So I think this is a solution, number 2. So this, how much time do I have? 5? Including discussion. Okay. Okay, so this is our latest experiment. We have just used a ball, solid ball, and this guy is imploded by Gecko 12, green line. And this is a fast ignition experiment. And this is a cone. And I'm sorry, it's a main story of this talk. This is a capacitor coil to generate a kilotesla magnetic field to collimate electron toward a compressed core. And the final result shows we could succeeded to hit the compressed fuel to almost 2 keV temperature. You can see here lithium-like and helium-like copper lines appear. That is a very good indication of a high temperature. So, in summary, capsule internal defects can be a source of strong radiator instability, and mode amplitude of these defects are well above NIF spec, so it's bad. And 3, the internal defects are large enough to quench ignition burn. And solution 1, emulsion technique, is in nature free from the internal defect. And solution 2, revisit sphere implosion, like Kida's idea, that is free from radiator instability. And we have, especially NIF, we have an ignition program, but this is a Chinese saying, Chinese painter draw dragons without eye. So that dragon doesn't move. But finally he put the dragon's eye, then that dragon flowing out. So we have to make a dragon's eye. Thank you very much.
All right. So this paper is